How are you, everyone? Good. I think I'm getting sick again. Today, my throat is aching, like itching, like some feeling I cannot describe. So I feel like probably I'm going to get cough, and cough means I'm getting sick for at least a week, 1 week or 2 weeks. It always happens. But anyway, so in our last class, we started vector space. Do you remember the video you watched in our last class? The animation video. So built on that, I'm not going to do much on vector space, just basic information on vector space. But before we start, does anybody have any question, comments, concern, complain, anything? Nothing? Okay. So Euclidean vector space, it consists of vectors, which are mathematical objects that have both magnitude and direction. So the magnitude means length, they have length and they also have direction. And we represent vector with an arrow on the top. Vectors are represented as directed line with arrows in R2, which is 2D, and R3, which is 3D. And they are used to model physical quantities like displacement, velocity, force, electromagnetic fields, etc. The main key operations in R2, and most of them are also applied in R3, except the last one, is that if you have any two vectors, it's R2, that's why you have only two elements, X and Y. So U1 is X, U2 is Y. You can think about that. So we have two vectors, U1, U and V. They have component U1, U2, V1, V2. So basically we have 2 points. In here, instead of points, we use vector. We write them as a vector. So they are column vectors. And if we have them, then they're equal if each component are equal to one another. So U and V, they will be equal to one another if U1 equals V1 and U2 equals V2. So basically X1 equals X2 and Y1 equals Y2. Then if you add them, it means you're supposed to add their components. So U1 plus V1, U2 plus V2. Or you can think of this as X1 plus X2, Y1 plus Y2. You get a new vector from the sum of the two vectors. And we can also subtract them, one minus another. So vector subtraction, it means basically you take one vector and then you change the direction of the other vector and then add two of them. This is what vector subtraction means. Scalar multiplication, just like the matrix multiplication. When you multiplied a matrix with a scalar, you multiplied each component. So this is also the same thing we're going to do here. A vector times a scalar means you're multiplying every component of the vector with the scalar. And then the last thing is a norm. Norm is a fancy word we use in linear algebra. Another word for norm is the length. How long or how much is the length of a vector? So to find this length in this Euclidean vector space, all you have to do is take each component, square them, add them, take the square root. So square root of the sum of the squares of each element. 3D is a different story. We find norm a little bit different, I think. But here we are going to talk about R2 mostly, at least in this section, R2. And the norm, we represent the norm with two vertical lines on both sides. So it's double absolute value. And then to measure the length or the norm, the square root of the sum of the squares. The vector norm is a measure of the magnitude of a vector. So that norm has another name, magnitude. the length. So magnitude, norm, length, they all mean the same thing. Now, we actually have most well-known vector norm are three types of norm. One is L2, which is the Euclidean norm. Then we have L1, which has another name, Taxicab norm. And then we have infinity norm. So the Euclidean norm, the L2 norm is, this is what basically we do. And fancy way to write this is, it's saying take the sum of all the elements row-wise, column-wise, and then take the square root. This is what it means. Okay. So when you go to linear algebra, if you take linear algebra, most likely we will not see this often. You're going to see this definition often, but they're the same thing. This is similar to the Pythagorean length. So basically, do you remember when we have what do you call it? Right triangle, then to find the length of the hypotenuse, we do a square plus b square, and then take the square root. This is exactly the same what you're doing here.
It's just the squares of all of the
Elements.
The squares of the
And then take the square root. For example, here we have a 2x2 vector. Sorry, a 2x2 matrix. So we have two vectors, and the norm of this matrix is 1 square, -2 square, -7 square, -3 square. You add all of them, take the square root, and whatever we have, that's the length of this matrix. Matrix sound weird. We call it vector. Then for L1 norm, we don't do exact same thing as L2 norm. In L1 norm, what we do is we take the sum of each element, the sum of the absolute value of each element. Okay. So in L2 norm, we square each element and we take the sum. But in L1 norm, we only take the sum of each element, but their absolute value sum, not their individual sum. In other words, what we do is we take the sum column-wise, and we take the sum column-wise in L1 norm. On the other hand, in the infinity norm has another name, maximum norm or max norm. So the word max is telling us what to do. We take the max of each row. And if you have many rows, so you add all the components in each row, and then you take the maximum column-wise, but you add all the rows. It sounds weird.
I'm a little confused because you're talking about vectors, but then you're also talking about.
Vector has 3 types of length, depending on what type of vector you have.
So there are vectors that look like a matrix? Is it the same thing as a matrix?
So matrix has, I think if you have a matrix, it's just vectors in columns. So 2x2 matrix means you have 2 vectors together in one matrix. If I'm not wrong, here's what it means. I have to search about it more, sorry. But here, what you're talking about is this, for individual vector, how do you find the length? So if you have only one, if you have in Euclidean, which is L2 norm, to find that, we consider it as the length is considered as a triangle. So to find the direct length from one point to another point, which is the vector itself. So remember, the vector starts from the origin. right? And then the tip of the point is whatever we have for the vector, the name of the vector or the component of the vector. So how much is the distance from the origin from the origin to that tip, that length in L2 form, in L2 norm. So to get that distance from origin to that, this is what the length is. So to find that length, we measure the x length and then the y length. So that square plus that square, and then to the square root of their sum. So this is the normal L2 norm what we usually use. There are also other two things we use, not as often as we use the L2 norm. We use L1 and infinity. So if you're working with L1 norm, all you have to do is you look at all the columns and you do column-wise sum. So you add all the components in the column, and then you take sum of the absolute value of all the columns. Let me do an example. It's easier. So we have 3 matrices, 2 by 2, and then 3 by 3. So for 2 by 2, if you want to find the L1 norm, it's maximum of the columns. So you add the column components, and whatever gives you the maximum number, that's the length for that vector. And if you want to find infinity norm, you do the other way around. You add all the rows, and then you take the maximum of their sum. So for this one, you add, when I say add the component, it means add the absolute value of the component. So we never subtract, we always add all the numbers. So we have 3, 6, -1, but we don't take negative, we take +1. We add 3, 6, 1, and then 3, 1, 0, and then 2, 4, 7. Now among all 3 sum, whatever is the maximum, that's the length for infinity norm. And if you're finding the L1 norm, then you do the other way around. You add each column and you take the maximum of the column. That's the L1 norm. So L1 takes maximum of the column. Infinity takes maximum of the rows, sum of the rows, sorry. And the normal one, the Euclidean one, what we usually use is every component square. You add them, take the square root. So depending on what they're asking, find L1 norm or Euclidean norm or L infinity norm. You use 3 different methods. Okay. Little bit clear? What is confusing? Columns. I mean, here it says add everything. So this is a column vector. So when you have 1 column vector, you add everything. But look at here, we don't have 1 column vector, we have 2 in matrix form. So when you have 2 in matrix form, you add everything and then you have to take the maximum of that. So you have only 1 vector, you add everything. But if you don't have a vector, you have a matrix itself, then you look at every column as 1 vector. And you add all the column individually, and whatever gives you the maximum, that's the L1 norm.
So like, let's say for A, if column 1 is bigger than column 2, I just take column 1.
Column 1, that's the length. That's the length of your vector. Yeah, for infinite, it is the other way around. You look at each row, and whichever row gives you the biggest sum, that's the length.
What is maximum outside of the
Maximum of the sum. So if you observe for this one, you're adding 2 plus 3 and 8 plus 1. So maximum of the sum, 2 plus 3 and 8 plus 1. This sum, 2 plus 3 gives you 5, 8 plus 1 gives you 9. So what is the maximum between 5 and 9? So our length is 9,
So it's just a bigger.
the biggest number.
What's the the seating? Like the bottom?
Euclidean norm, which is L2. So either they write L2 or only 2 here, or they write E is a Euclidean.
That expression is. Yeah.
So, so the length of the C matrix, which has 3 column vector, is sum of every element squared and then the square root. So if you want to take let's say L1 norm here, then you add all these columns, and then whichever column is the maximum number, that will give L1 norm. If you want to find infinite norm, you add all the rows, and whatever row gives you the maximum number, the CL infinity norm.
Okay.
And if you want to find the direct distance, then you add all the components, square, add, and then square root. Set a professional, no problem. What is this? How do I get rid of that? Oh, okay. Example, let's say we have x186. So some book they use the transpose to represent the vector, or some book directly this is the vector matrix vector. So 860, it means 86 transpose. So this is row wise. So when you transpose it, it becomes column wise. So row wise vector, this is column wise vector, the same thing. So you have 2 vector, x1 is 86, x2 is 4, -1 in R2. R2 meaning 2D space. In 2D space, we have 2 vectors, and this is asking first find the length for each vector, and then add the 2 vectors. For the new vectors, for what you receive from the sum, find the length for that vector, and then compare the two lengths. Which one is bigger or which one is smaller? Or do they have any relationship? So,
Would you remember to record?
yes, it is
Oh.
recording.
Sorry.
Thank you. So we have x1 as 8 and 6, and they didn't mention which norm, but the hint I believe is here, R2. In R2, we usually work with L2 norm, which is the Euclidean norm. It means you take each element, square them, and then add them, and then take the square root. So square root of 8 square plus 6 square. 8 square is 64, and 6 square is 36. So we have square root of 100. And what is square root of 100? 10. So the distance from 0 to 86 is 10 units. Now x2. Why it's so light? X2 is the same thing. You take each component, so 4 square plus -1 square. So we get 16 and 1, which is square root of 17. Do you know how much is approximately square root of 17 without using calculator?
4.1 something.
4 point something. Is it 1? I'm not sure about the 1. It's definitely 4 point something. How did you figure that out? So 17 is between 16 and 25. So if you want to find the square root of 17, that means you take the square root of 16 and 25. This gives you 4, this gives you 5. So square root of 17 is definitely between 4 point something to 4.999. It's between 4 and 5. So the first vector has length 10. The second vector has length 4. And now they're asking us to add vectors and find their sum. Sorry, find their length. So B is asking for a new vector, which we receive from adding the two vectors. So first vector is 8, 6. And you are adding 4 and negative 1. So what's the new vector? 12, 5. Good. So you add component 8 and 4, 6 and negative 1. Now to find the norm, oh, I should use the double thing. X3 is square root of what? What's the norm for X3?
What is it?
12 square plus U and 5 square. So what do you have? 149.
No,
144 plus 25. 169. And what is 169? 13. So x1 is 10, x2 is 4, and their sum is 13. So when it says how does the how does its length compare with the sum of the lengths of x1 and x2? Basically they're asking compare the three things and see what do you notice. So we observe that the sum, which is x3, has the longest length. I forgot my M. Right? X3 is 13, x1 is 10, and x2 is 4. So x3, which is the sum, has the longest length, or the largest length.
So it's asking, how does it compare with the sum of the lengths of 1 and 2?
The sum is this one. X3 is the sum. Oh,
Its length is the 13.
so, okay. So if you compare these three, the sum vector has 13, the longest one. Now, what if you add these two?
Right. I think that's what it's asking.
So sum of x1, oops, double, and x2 is 10 plus 4, which is 14 point something. Now, individually, if you compare them, this one is bigger, the sum of the vector is bigger, but when you compare the sum itself, the individual sum, so the sum of the individual length compared with the length of the sum, which one is bigger? The sum of the individual length. So we say sum of their length, sum of their norm. Sum of their norm is bigger than norm of the sum. Yeah. Norm of the sum. Right? Sum of the norms, which is this, is bigger than the norm of the sum. Any question? Okay. And then we have vector space. So once you know what vectors are and how vectors work, then we can work with vector space. So vector space is set of objects called A vector space is a set of objects. Those objects are called vectors that can be added together and multiplied by a scalar in such a way so that the addition, the sum, and the product will be within the space itself. Plus, though they will satisfy a set of axioms. This operation must be well defined. It means if you take any two vectors from the vector space, add them, the resulting vector has to be inside your space. Also, if you take one vector from the space and multiply by any constant, the scalar product has to be within your space. This is what well defined means. For instance, let's say you have a vector space V, and then you have a vector X in it, and you have another vector Y in it. So if you take X vector and Y vector from your vector space V and you add them, the sum has to be inside your V. For example, let's say this is a vector space. Here is your X vector and here is your Y vector. So if you add these two, the sum has to be inside. So X and Y, X plus Y. This is X, this is Y. The sum has to be inside your space. And if you take any constant scalar and multiply with a vector, the result also has to be inside your vector space. Then what is an example that is not a vector space? For example, let's say you have a set where first element could be anything, but the second element has to be 1. Okay? So a vector that has first component real number, any real number, and the second component is always 1. Now, 3,1 and 5,1 are two examples in this vector space. So in this vector space, you take two vectors. One has the first element 3, the other one has first element 5, and they both have second element 1. Now, this one is saying if you add the two vectors, the result has to be within your space. That means if you add the two vectors, your second element still has to be 1. But look what happens. When we add the two vectors, we get 8 and 2. 8, 2, even though 8 is inside the space, but 2 is not inside the space. So 8, 2, the new vector you got, it's not inside this set. This set has to have the second element 1. It cannot have anything that is not 1. So the sum doesn't give us a second element 1. So these two vectors are not inside a vector space. I mean, the sum is not inside a vector space. So this is not a vector space, even though we assume it's a vector space, but actually it's not a vector space. Yep. Any questions so far? So A space is a vector space. If you take any two vectors, add them, and the sum is also inside the vector space. It means if you take any two vectors that have the same property as your vector space, then when you add them, they also have to have the same property as the original ones.
Like,
This is an example. Oh,
like a book.
for example, let's say W, let's say U is a set with all the vectors. The first element is 0 and second element is A, anything. So if you take two vectors, E1, it has 0, 1, and let's say take E2, which has 0, 3. So if you add them, E1, I should do it here. E1 plus E2, you get 0, 1 plus 0, 3. What's the sum? 0, 4. So this vector, does it still have the first element 0? So it's a vector space. The second element could be anything. The first element has to be 0. So just by one of them is not satisfied. You have to check both of them. If you multiply any of the vector, let's say you're multiplying the first vector by 7. So 7E1. If you multiply 7E1, you get 0 times 7, 0. And then 7 times 1 is 7. So is 0, 7 still inside your U vector space, U space? So it's satisfied both conditions. That means the space I chose is a vector space.
I have a question.
Hmm?
Is that like the only way, or maybe like vice versa as well?
What do you mean?
Like, let's just say it was A0. Okay.
I just picked
Yeah,
a random one based on that one.
They,
So like R squared. Vector space.
It has to have some condition, right? I mean, some condition attached to it. Normal R2 means bunch of points. Well, yeah, it doesn't have any condition, like the first element or second element has to be anything. So yeah, R2 is a vector space. What does that mean? So R2 consists of all points, right? Any point here, there. So if you add any 2 points, you get another point. If you multiply a point by a constant, you still get another point. And all those points is still inside your R2 space. So R2, R3, they all are vector space.
How do we know, like, is this given to us, like, let W equals A1, is that given to us, or do we have to do?
If they give you, then all you have to do is check for the conditions, if it's a vector space or not. And if they ask you for an example, then you have to find an example which satisfies these 2 conditions. So in the exam, they will give you a vector space and they will ask you, they'll give you a space and they'll ask you, is it a vector space or not? So you have to verify that.
So these 3, 1, 5, 1, 8, 2, those are not points, they're vectors?
Vectors.
But they're not written
They're not
the
written in the
square-
point format.
square brackets.
Yeah, because I don't know why,
Okay,
but
okay.
we assume vector space consists of vectors and vectors should be written as squares. But yeah, at least they should have put some transpose so that we can see their vectors. But anyway, so the first 2 conditions, they have to satisfy these 2, and then they also have to satisfy, as long as they satisfy these 2, they will satisfy the other 8 of them. Not 8, sorry. This 2 is already inside this 8. So these axioms are saying, if you add 2 vectors, x plus y, this is same as you're adding y plus x. And the sum will still be in your V, in your vector space. If you add 3 vectors, the order how you're adding them doesn't matter. You can add xy first and then z, or you can add yz first and then x. And then there still will be in your vector space. If you take any element 0 and add 0 with your vector space, it will still be the vector itself and inside the vector space. So if you take any vector from your vector space, all these conditions, the result has to be inside the space. This one is saying the distribution. A constant times the sum of the vectors means you are multiplying each constant by the vector and then adding them. Or the sum constant, the sum of the constants multiplying the vector means you are multiplying each constant by the vector and then adding them. 1 times any vector is the vector itself. So they are like normal algebraic operations, but here we assume all of these are in vector form. So there are a few important vector spaces we have. One of them is C of AB. It means a set of all continuous real valued functions that is defined on a closed interval A to B. Or P of n, it means a set of all polynomials of degree at most m with real coefficients. So these are some examples of vector space. Solve the polynomials. When you add polynomials, you get a polynomials. When you multiply a polynomial by a constant, you still get a polynomial. So polynomials are vector space. Or continuous function. If you add to continuous function, you get a continuous function. If you multiply a continuous function by a constant, you still get a continuous function. This is basically what it means. The two examples of vector spaces. Any question? No? Okay, now it's time to watch a video. Now this time you're going to watch a video on subspace. So we know what is vector space. What else? Go to the subspace. What is a subspace? What do we do in there? Ready? Go. Where can it go?
Let's check out some spaces.
He knows a lot about all kinds of stuff. Professor Dave explains.
We've talked a lot about vectors and matrices lately, as well as how certain mathematical operations like addition and scalar multiplication work on them. Now we want to generalize these operations to define what is known as a vector space, which is sometimes also called a linear space. So let's look at this concept now. Before defining anything, let's just introduce some notation. Let's call our vector space V. If some vector is a member or element of V, we can denote it with this symbol here. So the following means that A is an element of V. All elements of the vector space have the same properties we already discussed for vectors. So elements must abide by the commutative and associative properties of addition, as is shown here.
We're EF Ultimate Break, the best way to see the world for anyone 18 to 35. We handle everything.
There also exists a zero vector in the vector space such that any element plus the zero vector will just give back the element. For each element A, there exists another element, negative A, within V, such that the addition of the two gives the zero vector. Scalars can be distributed across the addition of two members of V, just as an element can be distributed across the addition of two scalars. The product of two scalars multiplied by an element is the same as one of the scalars times the product of the other scalar and the element. And finally, multiplying by the scalar 1 just gives back that element. So these are simply properties that elements of the vector space must possess. And in this way, we can regard a vector space as a collection of elements that can be added together in any combination and multiplied by scalars in any combination. Now, an important property of a vector space is something called closure. Closure requires two properties. First, for an element A of V, multiplying A by any scalar will give a result that is also within V. Second, for any two elements A and B within V, adding the two elements will also give a result that is contained within V. These closure properties are what determine if V is a vector space. Let's take some time to examine these properties. At this point, it will be useful to introduce this R symbol, which represents the set of all real numbers, meaning positive, negative, rational, irrational, all the real numbers we talked about when we discussed the types of numbers in a previous tutorial. We can pick any element of this set, a real number, and multiply it by any scalar we want. Let's take the number 5 as our element and multiply it by a few scalars. 2 times 5 is 10. 8/3 times 5 is 40/3. 1/9 times 5 is 5/9. Pi times 5 is 5 pi, and so on. Notice that all of our results are still real numbers. This is because no matter what we choose, a real number times a real number is still real. So the set of real numbers satisfies the first closure property. Now for the second property, we will need to choose two elements to add together. we could choose 74 and negative 10, adding them together to get 64. Adding 2 and 4/5 gives us 14/5. No matter what two real numbers we choose, the sum of two real numbers is still real. So because the two criteria have been met, the set of real numbers is closed and can be considered a vector space. Moving to another example, let's expand on our notation. If R is the set of real numbers, Rn is the set of real vectors with a length of some integer n. Similarly, Rm by n is the set of real m by n matrices. First, let's just look at R3 vectors. We can multiply any such vector by any scalar and find that our result is a vector of length 3, made of real numbers. Similarly, we can add any two elements and find the same to be true, given that each component is simply now a sum that will result in another real number. This set is closed and is thus also a vector space. Given what we know about matrix addition, if some set is comprised of matrices with the same dimensions, multiplying by some scalar or adding any two matrices together will not change their dimensions, which makes this too a vector space. So it would seem that vector spaces can actually be made of more than just vectors. In fact, we could define a vector space that was made up of functions if we wanted to. For example, let's take the set of linear polynomials in the form of ax plus b. If we multiply by a scalar c, we can distribute to get ca times x plus bc. Since we are dealing with real numbers, ca and bc will also be real, and the form of our equation is still a linear polynomial, so our result is still within the set. Similarly, if we have two different equations, a1 times x plus b1 and a2 times x plus b2, and we add them, once we group like terms, we get the quantity a1 plus a2 times x plus the quantity b1 plus b2.
What if you can create your own website by saying, this is what I want? With Wix, you can. First up, let's talk about AI color themes. You can get any combos you want, bold and bright, minimalist and sleek, or something you didn't even think of. Just describe the vibe you want, or even use the colors of your logo, and let AI do its thing. Beautiful. Next up is the AI section creator. This is great for those website essentials, like a contact section, or a place to subscribe.
Once again, all of these are real numbers, and we get another linear polynomial that is contained in our set. With these two closure properties satisfied, we therefore have a vector space made of functions. We've listed a lot of examples of vector spaces now, so what does it look like when the closure properties are not satisfied? Take, for example, a simple set made of vectors of length 2. However, all the elements of this set have a value of 2 in the second row. Let's take two elements of this set, A and B, and try adding them together. We don't even need to assign values for the entries in the first row to see what will happen. The first row will be the sum of A1 and B1, while the second row will be 2 plus 2, which is 4. Our starting set only contained elements with the value 2 in the second row, but when we added two vectors of this set, we got a 4 in the second row, which means the sum is not a member of the set. Thus, the set is not closed and is not a vector space, despite the fact that it is made of vectors. A lot of the topics we introduce in the coming tutorials will involve working with vector spaces, so let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
With Google Play Games, you can play unlocked.
Professor Dave here. Let's talk subspaces.
He knows a lot about all kinds of
That is our next topic,
Professor
subspace.
Dave explains.
Once we understand what makes up a vector space, it is fairly easy to understand the concept of subspaces as well. To put it simply, a subspace is a smaller set within a vector space that is itself a vector space. Let's look at some examples to clarify. Let's say that V is a vector space. Now we can highlight this smaller section of V and call it S. Every element of S was already also in our vector space V, so we know they all obey the properties we discussed in the previous tutorial. This means that the only requirement we need to check in order to determine whether S is a vector space is that it satisfies the properties of closure. If S is closed, it will also be a vector space, and because it is completely contained in the larger vector space V, we will then call it a subspace of V. We saw last time that R3, or the set of all real vectors of length 3, was a vector space. So now let's look at a specific choice of vectors contained within R3 and see if it makes up its own vector space, thus qualifying as a subspace of R3. For this example, we will choose a set S made of vectors that have the form x, 0, negative x. By limiting the form of the vector like this, we have chosen a smaller set of R3, while knowing that our chosen set of vectors still follows the rules of the larger set. What we must check now is if our smaller set is closed by checking the two properties of closure. First, let's multiply a vector x by a scalar c. Distributing the scalar c, we end up with a vector cx, 0, negative cx. Notice that this still has the same form that we want for our set, with some value on the first row, 0 for the middle row, and the negative version of the first value in the third row. This vector is therefore still in our set S. Next, let's take two vectors, x and y, both from the set S, and add them together. Provided that we factor the negative sign out of this sum, we will see that the third entry is simply the negative version of the first, and once again, we find a result in the same form as we started. This means that the sum is also contained in our set S. We have verified that S is closed, making it a vector space, and because it was contained within the larger vector space V, this makes S a subspace of V. Before going further, it's important to introduce a few more concepts. Once again, let's say we have a vector space V and a number of elements of V, which we can call V1, V2, all the way to Vn. Any sum of these elements multiplied by some scalars, which we can represent as A1, V1 plus A2, V2, and so on, up to An, Vn, is called a linear combination. The set of all possible linear combinations of these elements is called their span. As an example, let's take three vectors from R3, those being 2, 1, negative 1, 0, 2, 2, and negative 1, negative 1, negative 1. The span of these three vectors will be given by the linear combination AV1 plus BV2 plus CV3, where A, B, and C are all scalars. Let's plug in our vectors and distribute the scalars, and then do vector addition to see that the span of these three vectors has the form 2A minus C, A plus 2B minus C, negative A plus 2B minus C. It's worth noting that the span of any number of elements of a vector space V is also a subspace of V. In fact, it is the smallest subspace of V that contains that set of elements, as it is the intersection of all subspaces that contain them. Span will end up playing a significant role when it comes to completely describing vector spaces, but for now, let's check comprehension. For more tutorials. Thanks for watching, guys. Subscribe to
Those, post those videos. Thank you.
Okay, so subspace. So now you have some idea what subspace is. Oh, before I forget, let me take the attendance first. Brandon C. Excellent today. Joseph. Justin. Gibran. Shivu here. Michelle. Jack. Ashif. Darius. Winston. Abigail. Shane. Emily. Kanar absent. Christine. Edison. Maisha here. Brendan here. Elvin here. Shafal. Absent. Alexander here. Shitila here. Wenchuan. And Kaiwan here. Let me remind you, your attendance is 5% of the grade. If you forgot. I mean, not you guys. Whoever is watching but not here. Our attendance is 5% of the grade. Okay, so if S is a non-empty subset of a vector space V, then it will be a subspace of the V if you take any two vector in S, add them, that result in S, and multiply any vector with a scalar, that result is also in S. So basically, the subset satisfies the bigger vector space. If you have them, then that S is a subspace. And remark, every subspace is a vector space. Every subspace of a vector space is a vector space in its own right. So the subspace of a vector space is a subspace. Sorry, is a vector set, is a vector space itself. And we can we can argue that it's true because any type of subspace you have, they have a zero space in there, the zero vector in there. So in a vector space V, it can be readily verified that 0 and V are subspace of itself. So if you have a zero vector, it's a subspace of the V, and if the V itself is a subspace of V. All the other subspaces are referred to as proper subspaces. We refer 0 as a zero subspace, and zero vector is a vector with a zero magnitude. So what is zero space? What does zero vector mean? Zero vector means it doesn't have any magnitude, means it doesn't have any length, and it doesn't have any direction. So it's a vector without any length or without any direction. So basically it's actually a point. This is what it means. We represent the zero vector with a single point. To show that a subspace S of a vector space forms a subspace, we must show that S is non-empty, and then it's closed under addition and scalar multiplication. So if you want to prove that A space is a subspace of a vector space, first thing you have to prove that it's non-empty, means 0 is in it, and then it's closed under addition, means take two vector, add them, the result should be within your space. And then scalar multiplication, the same thing, take a vector, multiply by any scalar, the result should be within your space. example. Determine that, determine whether the following sets form subspace of R2. So we'll be given few sets of examples, and how do we determine whether they are subspace or not of R2 is that first you have to show that 0 is in our set, and then any two vector, their sum is within the set, and any vector multiplication, any scalar multiplication, the result should be within the space. This is what we're supposed to show. And how do you say it in linear algebra language? It says it must contain 0 vector, it's closed under vector addition, and it must be closed under scalar multiplication. So these are fancy of saying what we're supposed to do here. Now the first example. Set of all the numbers, when you add them, the result is 0. Is this set a subspace of R2? The first condition, 0 has to be within the set. So if you take the first element 0, second element 0, and you add them 0 plus 0, then say 0. So we do have 0 in our set. Next, you have to prove if you take any two elements, the result has to be, the result has to follow this condition, satisfy this condition. So let's say we have U vector and V vector. U is U1, U2, V is V1, V2. So if you add them, since they are within the S, within the set S, so that means if you add these two, then say 0. If you add these two, then say 0. Okay? So our original set satisfies this condition. The sum of two elements always has to give you 0. And if you take two vector from that set, that means any two number you have in these two vectors, their sum has to be 0. So we are extracting, or we are collecting two vectors from this set. So first set is telling us that the sum of the U1, U2 is 0. The second vector is telling us the sum of the element is 0. Now, if you add U1 and V1, if you add U and V, you get U1 plus V1 and U2 plus V2. The two elements, right? These are the sum of the two vectors. Now, what is U1, V1? Sorry, we don't know what is U1, V1. But to add them, what we do, we add all the elements. It is the sum. We add all the elements, and when we add them, we can put U1 and U2 together, and we can put V1 and V2 together, because in addition, the position doesn't matter. So if you do that, U1, U2 is 0 because this is from the S, and V1, V2, the sum is 0 because this is also from S. So in other words, if you add the two vectors, the sum of the elements gives you result 0, which is within our set. The set says the sum of the vector has to be 0. So second condition we satisfied. Now the third condition says if you multiply by a constant, do you still have the result to be 0? So take vector V, which has two components, V1, V1 and V2, and multiply any constant C. That means you're multiplying V1 by C and V2 by C. So V1, C V1 and C V2. Now it says that the sum has to be 0. So let's add them. C V1, C V2. They both have C in common. So we have V1, V2. And since this vector V is from S, that means the sum of the component has to be 0. Because this is our condition for to be in S. The sum of the component is 0. That means V1 plus V2 is 0. We multiply C with 0, then say 0. So when you multiply C times V, you get 0. When you add any two vectors, you get 0. And 0 itself is inside this set. So this set satisfies all three conditions. So yes, this is a subspace of R2 with that has these conditions. Condition actually.
You go back to the condition one. Scalar is any real number.
Any real number. If you multiply the imaginary number, then we get problems sometimes, so that to be real. And that's how we prove any sets, okay? If you have any type of set, all you have to do is take these two examples, these three conditions, and then apply them and see what result you get. Then we have our next example. Ready? Think about this one. It's set of all the numbers. It's in R2. So we still have only two components in the set. It's saying that it's a set of all the numbers, their squares are same. When you square them, the results are same. I mean, when you square them, yeah, they're the same number. So it's only set of those now. It's only set of those vectors. When you square the components, you get the same thing back. So is it a subspace of R2? Who would like to try this? Basically, you're saying that show that three conditions satisfied or fail to satisfy. So what is the first condition? 0. So is 0 inside here? So 0 vector. So it has 0, 0. And we have 0 square and 0 square. So 0 square is 0, 0 is 0. Right? If both of them are 0, we have 0 square is 0. So first condition satisfied. 0 is, I should write this way. 0 is inside this set.
So does that line in this vectors?
Oh, this is just like implies. If both of them are 0, then what's the result we get? Oh, this line, the particle line.
Yeah.
It says, how you read it? It says, S is set of all the elements in 2D when you have x1, x2, given that x1 square equals x2 square. So this is like given that or such as.
What is the T refer to?
Transpose.
Oh, it's transpose, yeah.
So first condition satisfied, we have 0 in our set. What is our second condition? Closed under addition. So you take 2 vectors and prove that their sum square is, the squares are equal to one another. So let's say U is inside this set, and U has component U1, U2. What does that mean? It means U1 square is U2 square. If you take a vector from the set, the vector has to satisfy the same condition as the set. And let's take another vector from S. What does that mean? We have V1 and V2 in this vector. So V1 square is equals V2 square. Now what if we add them? U plus V. It means U1 plus V1, U2 plus V2. So if you apply the property, it says U1 plus V1 square has to be equal U2 plus V2 square if it's satisfied. Now we have to check, is this true? So let me go on the next page. U1 plus V1 square is U1 square plus 2U1 V1 plus V1 square, right? When you FOIL them, this is what you get. And we have U2 plus V2 square. And this means U2 square plus 2U2 V2 plus V2 square. Now we know U1 square is same as U2 square, right? Because this is their property. So if they both are same, they cancel out one another, right? Because they're the same. They can subtract the same thing from both sides. We also know V1 square is same as V2 square. Why? Because this is the property. V1 square is same as V2 square. So they also get cancelled out. Like if you subtract one from another one, they get cancelled out. They're same thing. So you're left with 2U1 V1 equals 2U2 V2. And this time 2 cancel out. So we have E1 V1 equals E2 V2. So what does that tell us? So are their squares equal? We know U1 square equals U2 square. But do you know U1 equals U2 or V1 equals V2? They individually not equal to one another, but their squares equal to one another. But here we got their product is equal to one another. So did it satisfy the second condition? We're supposed to have their square equal to one another. But we don't have their square equal to one another. So condition 2 failed to satisfy. So S is not a subspace of this. Are you guys lost? Kind of? Okay, let me see if I have. Okay, I have an example, a counterexample. So the two elements, they are not equal to one another, but they're square equal to one another. Now, for example, here, one square equals one square, right? If we have a vector 1, 1, they are inside our set because 1 square equals to 1 square. For example, let me write this way. So X is 1, 1. It means the first element square should be equals to second element square. It's true, right? Now we have another vector 2, negative 2. This is inside the set because 2 square is same as negative 2 square, right? So we got 2 vectors from this set. Now let's add them. If you add them, we get 1 plus 2, which is 3, and 1 minus negative 2, which is negative 1. Now, if this result, this sum is inside the set, that means 3 square. So we have 3, negative 1 as a vector format. So if it's inside the set, the condition says the first element square has to be same as the second element square. Is this true? Is 3 square is same as negative 1 square? No. So this set is not a subspace of the R2. So that's all for today. In our next class, which is next Monday, we are going to do a few more examples on subspace. And subspace is important because this will be in the exam. So we have next Monday, there is one homework, chapter 2, section 2.1, 2.2 by Monday midnight. So don't forget to do your homework, guys. Have a good weekend. Have a good night. Naisha, how are you?